Right, welcome back. Let's do question 12a. Right, but before we go to our question, let's just discuss about this concept. It's a bit difficult, but please try to take your time, and if it means replaying the video, please do so. Okay. Right, we're going to have three graphs here. The graphs of f of x, and then the graph of the first derivative, and the graph of the second derivative. And then we're going to look at the two situations when a is greater than 0, when a is positive, and when a is negative. Right, these are the three graphs. Right, let's start with the first one. This is the cubic graph. The cubic graph. Okay, it has what? Turning points and the point of inflection. The point of inflection is a point that is between, it's the midpoint between the turning points. It is the midpoint between the turning points. Okay, if you're looking at what? The x coordinates of these points. The x coordinate of the point of inflection is the midpoint of the x coordinates of what? Of the turning points. Now, remember that if a is greater than 0, the graph is shaped like this. It will be pointing, if a is greater than 0 means when a is positive, is pointing up, like the last part is pointing up like that. And then if a is less than 0, when a is negative, the graph will be shaped like this. The last part is pointing down like this. Okay, just remember that. So now, how will the graph of the first derivative look like? Okay, how will the graph of the first derivative look like? If you derive this cubic function, you'll get a quadratic function. So if you derive a cubic function, what do you get? You get a quadratic function. If you derive a quadratic function, you get a linear function. The turning points of the cubic function are the x-intercepts of the quadratic function or the first derivative graph. The turning points of the cubic function are the x-intercepts of the first derivative graph, which is what? Which is quadratic. This is the point here, this is the point here, which is going to be the x-intercepts of the quadratic function, which comes from deriving the cubic function. And then it will look like this. So now, if a is positive, if this a is positive, the first derivative graph is going to be concave up. If a is positive, the first derivative graph is going to be concave up. Right, and then the x coordinate of the turning point of the first derivative graph is equal to the x coordinate of the point of inflection. Just remember that. Okay, let me summarize what I've said so far. The x coordinates of the turning points of the cubic function are equal to the x-intercepts of what? Of the first derivative graph, which is the quadratic function, which is a parabola. And then the x coordinate of the point of inflection is equal to the x coordinate of the turning point of the first derivative graph. Okay, and then if a, the coefficient of x cubed, is greater than 0, the first derivative graph is going to be, or the first derivative graph is concave up. Okay, right, because the red graph, now I'll use colors now. The red graph is the derivative of the black graph, meaning that the red graph represents the gradient, or should I say gradients, because the gradients are changing here for this cubic graph. We don't have one gradient, it depends on the x value. So the gradients here are what? The red graph represents the gradients of the black graph. Okay, so at this point here, because the gradients are what? At the turning points, the gradient is equal to 0. So that's why this is the x-intercept here. At the turning point, the gradient is 0. That's why this is the x-intercept here. The red graph represents the gradient of the black graph. And then between the turning points, we can see that the graph is what? Decreasing, meaning that the gradient is negative. That's why between the turning points, this quadratic or the parabola is below the x-axis. It is below the x-axis. Remember that below the x-axis means that the y value is what? Is negative, isn't it? And then this side, going to the left here, we can see that the gradient of the black graph is increasing, meaning that it is positive. That's why the red graph here, from this point going this way, it is above the x-axis. Same this side, from this point going this way, the graph is increasing, meaning that the gradient is positive. That's why from this point going to the right like this graph is above the x-axis. Okay, right, let's go to the second derivative graph. Now, if you derive the first derivative graph, you'll get a linear function. So the linear function, I'm going to use the color blue. So the blue graph is the gradient of the red graph. The blue graph represents the gradients of what? Of the red graph. Okay, so where is the x-intercept of this linear graph? Where is it? At the turning point of the red graph, because at this point the gradient of this red graph is what? Is 0. Okay, since the blue graph is the gradient of the red graph, so it means it must be 0 there. So this will be the x-intercept of what? Of the second derivative graph. You see that? How can you remember this? If a is greater than 0, the second derivative graph is what? Is concave up. And the second derivative graph is increasing. The blue graph is second derivative graph. It is increasing. You can see that. Okay, you see that. So this is the second derivative graph, which represents the gradient of the red graph. Right, and you can see that at this point here, the gradient is 0. So that's why this point is the x-intercept. But to the left of this point, we are saying that the gradient of the red graph is decreasing. That's why the blue graph is below the x-axis. And then from this point, going from the turning point here, going to the right, the graph is increasing, meaning that it's positive. That's why the graph after this point here is also above the x-axis, is positive. It's increased, showing that the gradient is what? Is positive. Okay, so if you check the blue graph here, this side, to the left of this x-intercept, the gradient is negative. And then to the right, the gradient is positive because the graph is above the x-axis here. And then because here the graph is below the x-axis, that's why the gradient is negative. Okay, so I really hope that you've understood. So what have we learned? What have we learned? Remember this. The x-coordinates of the turning point of the cubic function are the x-intercepts of the first derivative graph. The point of inflection of the cubic function, the x-coordinate of the point of inflection of the cubic function is equal to the x-coordinate of the turning point of the first derivative graph. Then the x-intercept of the second derivative graph, in this case our blue graph, okay, is equal to the x-coordinate of the turning point of the first derivative graph and also a x-coordinate of the point of inflection of the original graph. If A is positive, the first derivative graph is concave up, the second derivative graph is increasing. Right, and then I really hope this will give us information that we're going to need when we answer our question. Right, and then the second part that I want us to discuss, when A is less than 0, this one will be fast because we've discussed most of the things when A was what, greater than 0. So when A is less than 0, meaning that when the graph is shaped like this, okay, right, still it's the same thing. The turning points of the original function will give us the x-intercepts. And then the point of inflation will give us what? Will give us the turning point. You see that? Okay. But if A is negative now, the first derivative graph is going to be concave down. It's going to be concave down, right? And then the second derivative graph is going to be decreasing. You see that? Okay, right. Now, I think now we can go to our question. Let's see. In the diagram below, the graphs of f prime x is sketched or represents the origin. Write down the gradient of f at x is equal to 0. So now, this is the graph of the first derivative. So this graph represents the gradient of the first derivative graph. So when you are reading from this graph, you are reading the gradients. When x is equal to 0, what is the gradient? The gradient is 15. When x is equal to 10, what is the gradient? The gradient is 0. Okay, because here y is 0. If x is 10, what is the gradient? The gradient is 0. So from this graph, the linear graph here, we are reading what? You are reading the gradient, not the y values, the gradient. Okay, this graph represents the gradient. So write down the gradient, even the instruction here. Write down the gradient of f at x equal to 0. This instruction is guiding us that you just have to read from the given graph. We don't need to do anything. Read from the given graph. So write down the gradient of f at x equal to 0. It means the gradient here is equal to, at x is equal to 0, the gradient is equal to 15. Right. Now, what type of graph is the original graph? The f of x graph. It is a parabola, isn't it? It is the parabola. And then the turning point is going to be by the x-intercept of this graph. Right. Before the turning point, the graph is above the x-axis, is positive. So it means the graph is increasing. Then after the turning point here, or after the x-intercept, the graph is below the x-axis negative. It means the graph is decreasing. You see that? So I can clearly see that the graph is concave down. Here is the turning point, then it turns and goes like this. Okay, right. You see that? So it means at x equal to 0, at this point, the gradient is 15. The gradient is 15 at that particular point there. Okay, right. So we're going to meet in our next lesson. I really hope that I managed to make you understand. Please try to replay the video if you did not understand. It may be a bit difficult to understand this concept. Thank you very much.